Okay, so today we move on to the second chapter of our book. And what we're going to talk about today is matrix operations. Now, I've already showed you all how to multiply matrices. So we'll look at this actually from a slightly different point of view and look at some other operations. But first, let's look at the anatomy of the matrix a little bit. So I'm going to introduce you to a little bit of terminology and what we call things. So if A is an n by n matrix, we will often write A in this form. And what this means is these are just the entries of the matrix. So basically think of it this way. Entry matrix, and if I have Aij, I is sort of the row address, and J is the column address. For example, if I make this matrix here, 1, 6, 2, 1, 1, 0, minus 1, 5, 6, 17. This is a 3-row by 4-column matrix. And for example, A, 2, 3, well, that's just reading your address here, will be in the 2nd row, 3rd column. So it's just a way to sort of see where everybody is in matrix. The diagonal entries are the ones where both the row address and column address have the same numbers, right? Now, diagonal entries are most interesting in actual square matrices, and that's what we focus on most. However, diagonal entries are defined for any matrix. Notice this matrix is not square because it's got more columns than it's got rows. But the diagonal entries are A11, A22, and A3. There is no diagonal entry in the last column because it's not square. As I said, diagonal entries are most interesting in square matrix. Called main diagonal. So, for example, the main diagonal here would be these 3 that I circled. And of course, the main diagonal on the square matrix is the most interesting. So, if a square matrix is called diagonal, if all non-diagonal entries are zero. So let me get a picture for you of diagonal matrices. And when you see them, you kind of look at it and say, well, of course, I see why they call this diagonal. That's a 2 by 2 diagonal matrix because everything that's off the diagonal is zero. That's a diagonal matrix. I mean, that's kind of stupid, right? Because my diagonal entries are zero, but still, it's a diagonal matrix. And there's a 4 by 4 diagonal. So everything's off the diagonal, and that's all it takes to be a diagonal. By the way, you all know, does anybody know a special matrix that's always diagonal? Anybody identify it? Yes. The identity matrix is always diagonal, right? Because what happens in the identity matrix, you have one side in the diagonal and zeros everywhere else. So that's kind of a big sort of encompassing example of diagonal matrices. However, the diagonal matrix, I'll give you one more that you look at and say here is a diagonal matrix. By the way, when I say diagonal matrix, I've already told you one thing, it's square as well as being diagonal. Is a scalar matrix. If all diagonal entries are the same. So, for example, that's a scalar matrix. Right. So it's diagonal, but everything on the diagonal is the same. So, for example, the identity is an example of a scalar matrix. Okay. Questions so far? Okay, more on anatomy before we all fly. So I'm not talking about diagonal anymore, so it doesn't have to be this matrix doesn't have to be square. A matrix is the zero matrix. If all entries are zero. What a shocker, right? We call the matrix zero matrix if all its entries are zero. And I'm going to say something else that I hope think is rather obvious. Well, so what do you suppose it takes two matrices to be equal? What do you suppose is the appropriate thing to say about two matrices whether they're equal?
have these scalar multiples of each other, because you can scale the other down.
It's more than the scalar multiples, because, for example, if you look at the identity matrix, now if you multiply that by 2, that's the matrix 2, 0, 0, 2. I don't think I'd want that to be equal to 1, 0, 2. So your condition is necessary, but you need a little bit more. That's too general, because actually there's some very different matrices. Unfortunately, the rubber is the same matrix. Obnoxious. It can happen. Let's not skip over something that's kind of obvious. Let me ask you this. In what universe would these two matrices? These two matrices be equal? No. And what's the first thing that's obviously wrong with them? They don't even match in size, right? Okay, so let's kind of state the obvious first. Two matrices are equal. The first thing I have to do is have them be the same size, right? Say both m by n, whatever n and n is for both of them at the same time. Now that you've got them the same size, what has to happen?
Symmetries.
You want all the entries to match. That's it, right? And 2, now that you know they're the same size, so this is the fancy math way of saying this, but really what this means is all entries. All. That's it. It's technical. Okay. Now, I will do this in simple form, at least the beginning, and I'll also have a parallel example. If A and B are both m by n matrices, then you can add them. Looks like A is Aij and B is Bij. Let me look at the example really quick. All right, it's down sort of motivated. Suppose I took 2 matrices. This is A and this is B. Now, be able to add 2 matrices, just like to be a pyramid, need to have the same size. Now, let's suppose that I wanted to add these matrices up. I want the output to be a matrix of the same size, 2 rows by 3 columns. And remember, in math, whenever you're doing things, it's not easy. What's the easiest way you can come up with new entry? Where do you feel it belongs here? Right, you just pair these off, right? 2 and 5 is 7. Then you get this 1, this would be negative 3, I guess. This would be 4, 3, 4. Do I see how? So, and notice this is why we need matrices at the same size, because you gotta pair them off to be able to add them up. So here's the things formula way. All this formula is going to tell me is to have the IJ entry of the sum matrix, just to add the separate ones. And that's all this formula means, is you just add, or you add it entry by entry. You can also take a matrix and multiply it by a constant. Let's kind of in parallel to that with an example too. You can also multiply the matrix A by a scalar C. So for example, if I give this matrix here, 1, 1, 4, 11, 12. Okay, here's a matrix. It's 3 by 2, 2 rows by 2 columns. What do you suppose is the appropriate way to multiply this by a constant? What if I want to multiply this by, say, 3? Okay, that's right. Just multiply every entry by the number. So E minus 3, 6, 12, 33, 36. Just like that. So C times A is C times matrix AI. Is matrix C AI. So you just multiply the secretary. Any questions? Okay. Now, we are going to record some rules, right? There's always kind of a rule. Make sure that's right here. There. But A, B, C. So let's suppose A, B, and C, these are all matrices that are in rows by columns. And R, S. So R and S are just numbers, just real numbers. So here are my matrix rules. Think about the way we added A and B here. Should it matter what order I add the matrices in? No, I'll get the same answer. Correct. Because all you're doing is adding up the entries, and it doesn't matter what order you add the entries in. So A plus B, B plus A, the same thing. Here's one from the lawyers here. 2. A plus B plus C is A plus. By the way, just forget it. Anybody know what that property is called? That's right. It's called the associative property. It doesn't matter. When you add 3 things, it doesn't matter which pair you add first. 3 A when you add the 0 matrix to any matrix, you get the matrix back, right? Because remember, the 0 matrix is the matrix that has zeros in every single entry. Right. Number 4. if you have the matrix A plus B, and you multiply it by the number R, what do you suppose this is equal to? Yeah,
RA.
correct, right. You want this to distribute out all nicely, and it does. By the way, these are all, if you dig on the math, these are all pretty easy to prove. And I'll skip over that, but if you're curious, you can come see me. You also get distribution of the scalars. And what I mean by that is if I have R plus S, just these two numbers added up times the matrix A, this is the RA plus SA. I'd certainly want that to happen, and it does. And finally, you get associativity with respect to multiplication. So if you take the number R times S, multiplied by A, this is the number R multiplied by S. Okay. Any questions? Okay. Now, let us jump to matrix multiplication. Now, I've already taught you how to do this, but we're going to take another look that hopefully will help solidify things. Think of this. Let me ask you the first quick question. I can add these two matrices, for sure. The multiply? No, they don't match for the multiplication that I taught you, right? By the way, suppose you have two matrices that you can add and you can multiply. What can you say about those two matrices? Square. The square. That's right. Okay, so let me kind of remind you here. Now, now, these two matrices I can multiply, right? Let's do kind of quick. What do you expect the output to be? It should be a 3 by 3. So go through first row, first column, should give you this first row, first column entry. So that's 1 minus 4 is -3. Then 0 is going to be -4. That's going to be -5 minus 14. Let's see, that's going to be 3 and 6 is 8. 6, that's going to be -15 and 1. 6. Finally, I'm going to 4, 14. 14. And 49 minus 20. I can actually multiply these matrices in the other order, but that time it'll give me a 2 by 2 matrix, right? Whatever. Now, here's another way to think about multiplication. And this sort of, so I just, when I told you how to multiply matrices, I just, we just did it, right? It's like, okay, let's do her. This is a bit of a justification why you do that. Think of matrix multiplication as a sequence of linear transformations. So let's let A okay, so let's let A be an n by n matrix, and let B be a n by k matrix. Notice that these are compatible. I can multiply A times B, right? And my output should be an M by K matrix, right? If you believe all the crap I did before. But unless K and M are the same thing, I can't multiply them in the other order. Do I agree with this? So let's let B be a vector. So this is a K row 1 column vector. Now, notice that BB, we've already done this kind of. You take this N by K matrix and multiply by this vector. This is actually and this is that stuff we were doing with linear transformation. So you can think of it this way. You start, say, maybe in RK, and here's your vector B that we had here. And B comes along and it does its magic. And it takes it to BB, and this is in Rn. Because when you multiply this matrix by this vector, this gives you a element Rn. This is like that linear transformation stuff we were doing before. Your input is V, and your output is BB, which lives in Rn. And you can do it again, can't you? Right? Because now this vector, this is a new vector right here, and there it is living in Rn, and you can come along and smack that up with A and move it on to Rn. So pick up where you left off here. And this is A, BB, and this lives in Rn. Yes.
Can you explain that?
Oh, maybe I screwed it up. Oh, which one?
The second row in the final column. In
The second row right here. So if I did it right, and we're probably fixing to see I made a
I got
mistake,
three.
it should be this second row times this column. So it should be 3 plus
Or I got.
6, which is actually 9.
Is
and
the
this
second entry in the row a 3?
I'm sorry?
Is the second entry in the row 2?
Oh, yeah, that's it. Yeah, there was a whirlwind there or something there. It was a 3.
I think the. Yeah, forget that. Thank you.
So one might ask, see how we did these linear transformations. First we did B, it knocks it here. Then we did A, it knocks it here. One might say, how could I just do B all the way over here in one step? And that is just multiply by the matrix AB. And so what should the matrix AB actually do? How can we make, so we can get B over here by first doing B, then doing A. What should the matrix AB be that knocks this all the way from RK to Rn in one step? And so how do we come to that? Well, notice we can write B as B1, B2, okay. Because actually B is an N by K matrix. So I've got K columns and they all should be in column. Everybody agree? Now, we can write B, vector B, that was I'll write entries of this. This is just a column of K numbers. Right. So when I did BB, when I did my first jump over here, then this is just DB1, DB. D1, B1, B2, B2, VA. So when I apply these columns to this vector, this is the way we multiply. So now I've got BV, which again has K columns, right? Determine this here. Okay. Now, what we can do is now apply A. Matrix linear transformation. A to BB dot. And what we did is ABB is equal to B1. Well, so think of it this way, A and this is a linear transformation, so I can split this up as B1 A B1 plus B2 A B2 DK. And this is properties of linear transformations from matrices, whichever you prefer. But the way you multiply matrix comes as sum of vectors. You can pull out the constants and you expand it like this. And so I can write this actually in our notation before as this is A B1 column, A B2 column, A B8 column times vector and so this sort of answers the question, because what this is right here is this is what I was looking for. This is the daddy Mac matrix. Takes B and pops it all the way over to AB. And so, conclusion. The matrix for AB, matrix that you get for AB, should be essentially positive. It should be just this this matrix made up of these columns. So it should be A B1 vector, A B2 vector, A. And this is an n by k matrix. Let me make a note of each A, B, and I. So that is each one of these columns, 81, 82, all of these, is a linear combination of column style. Entries of the vector B, I as weights. So notice this is exactly what we were doing before. This is exactly what strives, because each ABI is going to be B1 times first column of A, B2 times the second column of A, and so forth. And you actually get exactly the formula we had before. So let me do a sum that comes full circle here. If A, B, so space A is an n by n matrix, and B is an n by n matrix, then is a n by n matrix. And I can give you a formula for what the IJ entry is for this. A equals A by J, and B is equal to the, let's say, A, then the IJ entry so here's kind of a formula for it. But from a practical point of view, I still multiply it the way that we did in class. The formula just is kind of a nice thing for proofs, things for more general situations, but here it is. One B, one J, plus A, 2, B, 2 J, plus all the way up to A by M. That's exactly the row column thing that we were doing before. Notice there's a pattern here. If you like such things, notice this is the IJ entry, right? This is the IJ entry. Notice that the A's all lead with I's and the B's all book in with J's, right? And in the middle, you get sort of the crossing out like we do with matrix, right? We got a match here in the middle, we got a match here in the middle. And I know I go up to N because this has A has N columns, which is the same thing as the number of rows of D. Any questions? So this is mainly just kind of a verification of stuff that hopefully we already know. Let me give you some rules, some matrix multiplication, and maybe a word of caution about something you got to be a little careful about. Well, let's let A be I'm going to specify the size of A. It's in R n by n. B and C are matrices. Of appropriate size. And R is a good number. So R is just a number. And I'll tell you what I mean by the appropriate size here. When I say appropriate sizes, I mean that every time I write a product or a sum in this thing, then the sizes are right so that I can actually do the multiplications. So in the first A comes BC equals So by appropriate size, what I can tell you in this computation here is that N has to have, or I'm sorry, B has to have N rows, right, to match up with A. And however many columns B has is the number of rows C has. So I'm assuming it's multiplication is defined. So multiplication where defined must be associative to A equals. Notice the appropriate size here, all this means, it means two things. Both B and C have the same number of rows as A has columns, and B and C have to be of the same size. We're going to be able to add them up. So I've got that rule going for me. This may seem overkill, but it actually is different. Anybody, as far as size goes, can anybody tell me what one thinks the difference here? That's right, and that could make a difference, right? What this means is B and C have to be the same size, but now the number of columns of B should equal the number of rows of A, which was the opposite of what had happened here. This is BA plus CA. Before, if you have R, the number times AB, this is RA times B, and it's A times R. So I can slide that number in and out wherever I want. If I multiply A on the right side by the N by N identity, I get A. And that's the same thing as if I multiply it on the left side by the N by N identity. Okay. Any questions? Yes.
Are I sub N and I is sub N.
Yes, potentially. Because, for example, if A is a, let's say this is a 3 by 5 matrix, right? Then this would be 5 by 5 identity. And this would be 3 by 3 identity. So this would be smaller, right? Okay, so let me give you all kind of heads up here. We give you some quick examples here, point out some of the hazards. First is multiplying two matrices in different orders can even give you different sizes, perhaps. We've seen examples of that. If you multiply 2 by 3 by 3 by 2, you get a 2 by 2. Multiply the other way, 3 by 3. But even if they're square, they can be different. In fact, I had totally unlucky for my example of making it on the fly and work out. If you look at A baby, this is 1 minus 1, 2, 5, 1 minus 3, 1, 4. And this matrix is 1 minus 1 is 0, minus 3 minus 4 is negative 7, 2 and 5 is 7, and minus 6 and 20. Now, if you look at the other direction, be A. This is 1 minus 3, 1, 4 times 1 minus 1, 2, 5. This is going to be, let's see, that's going to be 1 minus 6 for the first. Well, it's already different. Right, I mean, I've already blown it because that ain't 0. Well, I'll finish this off. This is minus 1, minus 15, 16. This is 1, this is 9. This is minus 1, 2. Very different. Right. This actually should make sense though, because really matrices are linear transformations, and when you compose functions, you don't usually expect to get the same thing if you compose functions. Let me give you another couple of hazards here. Notice you often cannot cancel. That is to say, not always meaning that you can't cancel matrices. You know, I'll give you because oh, well, so also notice that non-zero matrices with product 0. Let me give you an example of this. In fact, this is the square of this matrix. All right. I'm going to call this A squared. On matrix A is a system right here. Notice when I multiply this, this row comes this column, it's 0. This row comes this column, and the twos miss each other. And then this row of 0. So notice I multiplied 2 non-zero things. In fact, I squared something to 0, and I got 0. That's something else that you have to look out. Okay. We'll talk more about this next time, but I want to give you one more thing to chew on, and that is notion transpose. If A is the matrix Aij, then A transpose is the matrix A. So you just reverse the roles of rows and columns. So if A is 1, 2, 3, 4, 5, 6, then A transpose first row here becomes the first column here, and the second row here becomes the second column. Right, pretty easy. You just turn rows into columns. Let me give you a couple of theorems. And A transpose. Okay, let me ask you this. What happens if you take a matrix and you take its transpose and then you take its transpose again? Where are you going to get? Back to where you start. That's right. 2. If you take A plus B transpose, this is, and of course, this assumes A and B are compatible. That is, you can add them. Number 3, if you have a constant times a transpose, this is our content control. And here's the last one. Again, assuming that A and B are compatible, that is, you can actually multiply them. Anybody want to guess what this one is?
Transpose.
Gosh, I wish, but not quite. Anybody want to guess? The problem is, if you multiply this, you might not be able to multiply a transpose. It's the product of transposes in the reverse order. I encourage you to just make up some small matrices and check that out. You can see if you can prove it, but do the computation and check that out. See why it is. Okay, questions? Any questions? Don't forget you got a quiz due tomorrow at 5. Other than that, y'all have a good one. We'll see y'all Wednesday.
How do you feel about the last quiz?